Okay, so we're going to move on to work and kinetic energy, which is chapter 6. And let's do some calculus-based problems. So 6.62. Unfortunately, I don't have the answer in the back of the book, so we'll just have to assume I do it correctly. Okay, it says a balking cow is leaving the barn as you try harder and harder to push her back in. In coordinates with the origin at the barn door, the cow walks from x equals 0 to 6.7 meters as you apply a force with the x component f sub x. How much work does the force you apply do on the cow during this displacement? So what we have is that the work is the integral of f dot dx, and it's a full-blown vector form. Because f and x are in the same direction, or at least in the opposite direction, then the dot product just gives us a -1 result. Because what we have, we'll just draw the cow as a box. So you're pushing backwards this way. So this is your force, which is a function of distance, f of x. And x is this way. So we start off at x equals 0, and then the cow keeps moving and you keep pushing. So this is the direction for x. And because the force and the displacement in opposite directions, we're going to include a negative sign. So the work is equal to negative the integral from 0 to 6.9 meters. And the force that I'm applying is going to be, well, actually it shows it in the given f sub x is negative, so we don't actually need a negative sign. So it's going to be equal to negative the quantity 20 newtons plus 3.0 newtons per meter times x, and then we multiply by dx. Again, the dot product comes out in this negative sign for the force. So what does this mean? It means, well, we're initially pushing with 20 newtons, but the cow's still moving forward, so we keep pushing harder and harder and harder. So all we have to do is just do simple integration now. The integral of 20 newtons dx, actually negative 20 newtons dx is 20 newtons times x. And then we have a negative sign because this negative applies to both parts. 3.0 newtons per meter times x squared over 2 plus, well, we don't, since it's a definite integral, we're going to integrate like this. So we just evaluated it at the upper and lower limits, so we get negative 20.0 newtons times, now I'm going to actually do the two parts together here, so I'll take 6.9 minus 0, so you get x at 6.9, x at 0. Then we have negative 3.0 newtons per meter times x squared. So we take 6.9 squared minus 0 squared divided by 2. And we should get a negative work. So our first term is 6.9 times negative 20. So it's negative 135, 138. The units are Newton meters. These are meters. These are meters squared. So, yeah. So we get here newtons times meters. Here we get newtons per meter times meter squared gives us Newton meters. And the second part is 6.9 squared times 3 divided by 2. So we get negative 71.4 Newton meters. In terms of work, units for work are did I do something wrong there? Oh, that's 138. Okay, so we get negative 138 minus 71.4. We can only actually carry this out to this place, which is the ones place. So we get negative 209 Newton meters, but Newton meters a joule. So it's kind of like friction. You can think of friction back in our algebra-based Okay, I got called away there, but I think I am at the end of the problem anyway. So we get negative 209 joules is done. The work done by me on the Cal is negative 209 joules. So again, work is force times displacement. When you have a varying force with x, you have to integrate. You integrate from the beginning value of x to the final value of x. Now the question is, you know, do I stop the Cal and start pushing it the other way back? I really don't know that. All I know is the amount of work that I've done during that process.